4.2 is exponential functions. We'll talk about some additional properties of exponents first. For any real number, a greater than 0 and a not equal to 1, the following statements hold. Properties: a to the x is a unique real number for all real numbers x. The description is that y equals a to the x can be considered a function f of x equals a to the x with domain negative infinity to infinity. Property B says a to the b equals a to the c if and only if b equals c. And we know that because the function f of x equals a to the x is 1 to 1. If a is greater than 1 and m is less than n, then a to the m is less than a to the n. For example, 2 to the third is less than 2 to the fourth. Increasing the exponent leads to a greater number, and the function f of x equals 2 to the x is an increasing function. However, if a is between 0 and 1 and m is less than n, then a to the m is greater than a to the n. For example, 1/2 squared is going to be larger than 1/2 to the third. This is because the a is a number between 0 and 1. So increasing the exponent leads to a lesser number. The function f of x equals 1/2 to the x, therefore, is going to be a decreasing function. If a is greater than 0 and a is not equal to 1, then the exponential function with base a is f of x equals a to the x. So an exponential function is where you have an x in your exponent. Sketch a graph of y equals f of x. Identify the y-intercept, domain, and range, and give the equation of the asymptote. So our first one is f of x equals 3 to the x. And what we can do to start graphing this is to make a t-table of values. We know that the domain is going to be all real numbers, negative infinity to positive infinity. So now that we have identified that, we can pick some negative numbers, 0, and positive numbers to use as our exponent. So 3 to the negative 2 is going to be 1/9. 3 to the negative 1 is 1/3. 3 to the 0 is 1. 3 to the 1 is 3, and 3 squared is 9. So I have these that I'm going to graph. And just smoothly connect those points that you plotted. And if we would continue to go to more and more positive x's, y just increases. So we put an arrow up to show that it keeps going that way. If we get more and more negative numbers, it's just going to make this an even smaller fraction. So we're approaching 0, but we can never put a negative enough exponent on 3 to make it be 0. So we have an asymptote there. That asymptote is the equation y equals 0. And our range then, we know, goes from 0 to positive infinity, not including the 0 because it never actually reaches a y value of 0. Okay, our y-intercept is 0, 1. And make sure that you write it as a point. There you go. Now if I have 1/3 to the x, I can do the same type of thing. I make a t-table of values. X can be any real number, so we have domain of negative infinity to positive infinity. So I'm going to put in these values again. So a good mix of negative numbers, 0, and positive numbers. And then I start putting those in. Let's start with 0 though. 1/3 to the 0 is 1. 1/3 to the 1 is 1/3. And 1/3 squared is 1/9. Now if we think of 1/3 to the -1, see, that's going to be 1/3 to the -1. To make that a positive exponent, we flip this fraction, and so it's just 3 to the 1, which is 3. And we do the same thing if we have an exponent of -2. So it's 1/3 to the -2. Flip the fraction, that makes the exponent positive, and 3 squared is 9. And you're seeing some similar values that we had over here, just placed differently. I have points of -2, 9, -1, 3, 0, 1, 1, 1/3, 2, 1/9, and this is another asymptote, and going this way. Okay, so we have a range again of 0 to positive infinity, an asymptote of y equals 0, and again the y-intercept is 0, 1. So have all of our information there, and you see here that these graphs are just reflections of each other over the y-axis. And one reason for that is that this 1/3 to the x can also be written as 3 to the -1 to the x, or 3 to the -x. So when you replace your x with negative x's in a function, it makes this graph resulting from this equation flip over the y-axis. It makes all of your y's the same, except that the x's changed sign. So we have a 9 came from a 2 over here, a 9 came from a -2. All right. Here you can see some families of exponential graphs. So y equals 1/2 to the x, 1/3 to the x, 1/5 to the x, and so on. And then these numbers that are greater than 1 to an exponent. So if you have a fraction to the exponent, it's going to be a decreasing function, a fraction that's between 0 and 1. And if you have a number that's larger than 1, then it's going to go increasing on its domain. Now let's try graphing this. And we can view this as a transformation. We had the t-table for this before, x and f of x t-table. We went -2, -1, 0, 1, 2. And when we put in 0 for the x, 3 to the 0 is 1, but we have to subtract 1 from that output, so we get a 0. If we put in a 1, 3 to the 1 is 3, but then we have to subtract 1 from that, we get 2. 3 squared is 9. Subtract 1, that makes 8. 3 to the -1, that's going to be 1/3 minus 1 is a -2/3. 3 squared is 1/9, but if I subtract 1, that's going to be a -8/9. Okay, and then I can graph that. -2, -8/9, -1, -2/3, 0, 0, 1, 2, 2, 8, and connect those points as smoothly as you can. Okay. And we know this continues to go up like that. What is happening over here? When we graphed this before, it without the -1, it was approaching 0 there. Now we're approaching y equals a -1. So we subtracted 1 from the original function. All of the y's get 1 subtracted from them. Even my points. This was a 9, but I subtract 1 from it. It was a 3, but I subtract 1 from it, and so on. So here we could go ahead and say our domain is all real numbers. The range goes from -1 to positive infinity. The asymptote is y equals -1, and the y-intercept also goes down 1 point, so it's 0, 0 now. Now the characteristics of the graph of f of x equals a to the x are that you have these points, -1 and 1 over a, 0 and 1, 1 and a. Those are all on the graph. If a is greater than 1, then f is going to be an increasing function. If a is between 0 and 1, then f is a decreasing function. The x-axis is the horizontal asymptote. Domain is going to be all real numbers in the range from 0 to infinity. So let's see if we can write equations for these graphs given the qualities that we know about exponential functions now. It's helpful to notice where the graph is approaching as we go to the left, that horizontal asymptote, but also to identify points. This is the point 0, 1. This is the point 1, 2, the point 2, 4, and I even have this point 3, 8 I can identify. 3, 8. So we can see that this f of x is equaling 2 to the x. If x is 0, then 2 to the 0 is 1. If x is 1, 2 to the 1 is 2. If x is 2, 2 squared is 4. If x is 3, then 2 cubed is 8. That's our function. This is a very similar function. Identifying the points, I have 0, -2. I have the point 1, -1. I have the point 2, 1. And if you look at these, the x values are the same as what I had in the graph at left, but the y values are, looks like 3 less every time. It's 3 less every time. The y values are 3 less every time. So this function is going to be the same type of growth, but the y value is always 3 less. So we subtract 3 from that entire g of x function. Alright, let's solve some equations, just some remembering some exponent rules here. If I have 2 fifths as my exponent, what I can do is raise both sides to the power of 5 halves. Okay, and so that is going to give me x by itself, 2 fifths times 5 halves, that's gone, is going to be, well, if I have a 16 to the 5 halves, that's a square root of 16 to the 5th. And don't forget the plus minus. When you put that 5 halves on there, since the 2 is in the denominator, you're making a square root. You're putting a square root on there. So you have to put that plus minus. So x is going to be plus or minus 4 to the 5th. So 4 to the 5th. You can put that in your calculator if you like. Use your exponent key. I get 1024, or a -4 to the 5th is going to be a -1024. And you can check that if you like, just to show yourself that it really does work, especially with that negative number. If you have a negative 1024 in parentheses and you raise it to the 2/5 power, then you will get 16 as in the original equation. Okay. So just remember, if you are raising to a power that has a denominator that's even, you're really taking an even root. You have to put plus minus. All right, on this one, x to the 7/5 is equal to negative 128. And what we'll do is raise both sides to the power of 5/7. And we do not need to put a plus minus when we take that root, because we're taking a 7th root. X is going to be a negative 7th root of 128 to the 5th. So you can take 128 and the 7th root of that, and get a 2. So this is going to be a negative 2. We still have to apply the 5th power, and we get a negative 32. And here you don't have to have parentheses if you don't want to do that. Okay. And here I have 1/32 equals x to the negative 5. So we can raise both sides to the power of negative 1/5. Again, we're taking an odd root with the 5 being on the denominator of that power. So we don't need to put plus or minus as we did in the first example. So x to the negative 5 to the negative 1/5 gives me just an x. And when I have a 1/32 to the negative 1/5, what that is going to do is make me flip the 1/32 to a 32, and then that makes my exponent positive. It's still a 1/5, so we have a 5th root of 32, which is 2. Right, here are a couple of formulas where exponential functions are used. The first one's compound interest. So if you take money and put it into an account that pays an annual interest rate that's compounded n times per year, after t years the account will contain a dollars according to this formula. A is going to be P, the principal that you put in, times 1 plus R, which is your annual interest rate as a decimal, divided by the number of times it is compounded per year, and take that all to the T, this is the number of years, times N, against the same N as this, the number of times it's compounded per year. If you are continuously compounding, then you would use this formula instead, and all you need for that is to know the principal and use the E that is in your calculator to an exponent of R, that interest rate given as a decimal, times T, and T is given in years. That will give you your maturity value, your ending amount. So we want to find the future value and interest earned if $56,780 is invested at 2.8% and compounded quarterly for 23 quarters. So let's first write the formula that we use. It's the ending amount is going to be your principal times 1 plus R over N to the Tn, and fill in what we know. We have $56,780 that we are investing, and it's invested at 2.8%, so 0.028 and it's compounded n times per year. Quarterly would be 4 times per year. And then it's compounded for 23 quarters. Well, how many years is 23 quarters? If we take 23 and we divide that by 4, that's going to be 5.75 years. And again, the number of times per year is 4. And all you need to do is put that into your calculator, 56,780 times parentheses 1 plus 0.028 divided by 4 with an exponent of parentheses 5.75 times 4 and close your parentheses, and we get $66,661.21. The number goes on in your calculator. Just make sure that you round it appropriately. Since we're dealing with money, we'll round it to the hundredths place, so that would give us the cents. Let's say that we were going to compound this interest continuously. So you're putting an account that's continuously compounding. You do that for 15 years. Remember that formula was A equals P E to the RT. The PERT formula, some people like to call that. Your ending amount is going to be the $56,780 times E times your to the exponent of your interest rate written as a decimal times the time in years, which is going to be 15 for us. So A is about, again, you can put this in your calculator, 56,780 times E to an exponent of 0.028 times 15, and we get $86,416.98, and put your label on there. Alright, so not only can we use the formulas that way, but we can find the amount we should put into an account in order to earn a certain amount of money by the end of our investment time. So that's what this next example is. Find the present value that will grow to $45,000 if interest is 3.6% compounded monthly for 1 year. Okay, so finding the present value that will grow to an amount of $45,000, and we're trying to find the present value, and that's 1 plus 0.036 divided by n is the number of times it's compounded in a year's time, and that is going to be 12, to the t, that's just our 1 year, and the n is again 12, the number of times it's compounded per year. So if I wanted to solve for p, then I would just divide by this 1 plus 0.036 over 12 all to the 12th, both sides. So I'm going to do that, and say 45,000, and I'm dividing that by 1 plus 0.036 over 12 to the 12, and so my principal would have to be about 43,411 and 15 cents. And if I would put that in now in an account that earns 3.6% interest and compounding monthly, then at the end of that year, then it will have grown to the 45,000 value for A. And that wraps up your 4.2 lecture. Go ahead and give your homework a go. Be sure and let me know if you have any questions.